You're the speaker? Yeah.
So, MacBook.
So can you, we have a Zoom thing. Can you join in our Zoom thing? Because they wanted to live stream it
Where?
in our YouTube channel.
Oh, okay. Fine. Zoom, yes, I can. I have internet, right? Internet,
You have Wi-Fi access?
yes.
Then you can join.
Okay, I want to put this on charge because it's going to be a long talk. Yes. So how this is my talk. So should I open it? This one? This one? This one?
அதான் மிக்சி காலையில போட்டுருங்க. சரி இப்ப என்ன பண்ணணும் அல்டிமேட்டா நீ வந்து எது போறதுன்னு தெரியும் இது தானே பண்ண போறேன் அல்ல நம்ம வந்து மற்றதெல்லாம் வந்து நான் என்ன கேட்டுதான் நீங்க நானே தான் வாங்கி தர மாதிரியும் இதுக்கு மட்டும் நீ என்ன டிபெண்ட் பண்ணிட்டு இருக்க மாதிரி நீ பேசுன போட வேண்டியதானே நீ அப்படிலாம் நான் அப்படிலாம் சொல்லவே இல்லை நல்லா இருக்கும்னா நான் சொல்றேன்.
Turn up volume. I cut it. Sure. Sure. Okay. So what should I do? Share screen. Fine. So now I open this one, right? This one. Where is it? Share screen. This one. But I have to go to full screen, right? Slideshow or full screen. This one. It's okay? Yeah. Okay. have a pointer.
Yeah.
Changing the slides. It works.
You have a connected,
What?
you have a connected with your laptop.
No. Here. How it works. This one. This one.
More well for you.
If the battery is working.
Yeah.
Slide is.
Sorry.
This will. Oh, fine. I can just look at it.
So nothing else.
Sometimes it's working.
Okay, but yeah. Biscuit put our meeting down. Bluetooth connect ஆகுமா என்னது ஒர்க் ஆகுதா இது வரைக்கும் டெஸ்ட் பண்ணவே இல்லை அது பாட்டு எடுத்துட்டு வெளில போயிடுச்சு கொடுத்துட்டு போய் தொலை வேண்டியதானே
அவசலையா
play காட்டு.
அது இந்த கனெக்டர் வேலை செய்யலையோ ஒரு வேலை ஆகுது ஃபுல் ஸ்க்ரீன் போடு ஆகல இப்போ ஆகுதா ஃபுல் ஸ்க்ரீன் போடு என்னாச்சு ஃபுல் ஸ்க்ரீன்ல இருக்கா கண்ட்ரோல் ஏ போடு வரலையா அந்த ஃபுல் ஸ்க்ரீன் ஷிஃப்ட் பண்ணாங்க Do I have to walk here or I can? You can walk. Okay. কবে করেছি 2017 2017 ডিএসসি কমপ্লিট করেছি মানে আমি সার্টিফিকেট পেয়েছি সেপ্টেম্বরে জুন ওই টাইপে কি সাইন করেছে সেন্টার ফর কন্টেন্ট টেকনোলজিতে এক বছর ছিলাম ইংল্যান্ডের সাথে হ্যাঁ 21 কোরিয়া ইনস্টিটিউট অফ
Audio. Okay, so it's a pleasure to have Srovona. Dr. Srovona Bakchi is a postdoc currently in the Korea Institute of Science and Technology. Srovona did her PhD with Professor Orenpati in HRI in 2017. And then she was a postdoc in Security Center for Quantum Technology in Singapore for a year. In 2018, from 2018 till 2021, he was a postdoc in Professor Lev Heidman's group in Tel Aviv University. And from 2021, she has been working as a postdoc in this group. So today it will be physics colloquium, and Friday there will be technical talk. So she is a faculty applicant.
So, good afternoon. It's a pleasure to present my talk here at your very reputed institute, INSC. So my talk is on quantum measurement kaleidoscope. By this I mean that I will cover all the different ways this measurement can be used for various applications. And also I will discuss some fundamental issues that still need more understanding and resolution. And all these works I present have been done some a bit in my PhD, then mostly also my postdoc years. And I elucidate more on my recent works. So let's plan of the talk. So I start with motivation. Why I think that the research on quantum measurement is very important. Then I will briefly discuss this quantum measurement formalism in non-relativistic quantum mechanics, which include the strong, weak, and reverse measurements. I will present one of my results, which was derived in PhD, reverse uncertainty relation. I will also discuss another one, which is inferred uncertainty relation. Then I'll go to quantum weak and reverse measurements and discuss about this work that I have been doing in Korea Institute of Science and Technology, which is inherent information loss quantification and its properties. I will talk a bit about another work that I am pursuing with my own students under a program. So it's quantum weak measurement result, some results from quantum weak measurements, and it includes quantum state estimation to quantum states will be using past and future measurements. So this is another way of using measurements for some applications in quantum physics. Quantum pigeon hole paradox, this is actually another application of modifying the interaction between quantum systems using the property of post-selection and weak measurements. I will briefly mention that this quantum reverse measurement can be used for improving the efficiency of quantum entanglement swapping protocol. Then I will discuss the foundational issue that I think is important, is that incorporating relativistic effects in standard formalism of quantum measurements. Why, how, and the current state. And I will end with future directions and conclusions. Okay, so motivation, quantum operations and quantum measurements are an important part of modern quantum information theory and quantum computation. This area is very well developed, studied in the non-relativistic quantum information using non-relativistic quantum mechanics. This means that all the experiments and this quantum information tasks are performed in the rest frame, and there is no relative motion between the different quantum systems. And study of these quantum measurements and operations have helped the development and implementation of various quantum information processing protocols such as quantum teleportation, quantum state estimation, quantum cryptography, and some instances of uncertain relations with quantum memory, and it has applications in cryptography, all those stuff. So, quantum measurements and quantum operations in general, well developed in non-relativistic mechanics, have been developed and understood in various contexts of quantum information protocols by varying different intrinsic parameters of the quantum measurement setup or the experimental setup, or by varying the order and manner in which these quantum measurements have been performed. So there is a lot one can play with using quantum measurements that can help in the various quantum advantage in these quantum information protocols. So this analysis will be helpful in the quantum technology sector. But let me say that this theory is not well understood in relativistic quantum information theory that uses relativistic quantum mechanics or that uses quantum field theory. So there are several less understood areas that require theoretical analysis. So I just mentioned one problem here very briefly, one such area in the relativistic regime, and discuss the underlying issue around it. So quantum measurement formalism and non-relativistic quantum mechanics so we know that it's an operation on a quantum system, such as the testing or manipulation of a physical system to get a numerical result, that we get a classical result at the end of it, which is a number or a meter or something. So the method for finding a probability of obtaining the outcome involves the quantum state and a mathematical representation of the quantum measurement, which is to be performed on the quantum system. So several formalisms for presenting quantum measurements have been developed, which have found relevant in different tasks. This includes the projective measurement, the POVM measurement formalism, weak measurement. There are other very interesting interaction-free measurement, which was proposed by Elizur and Weidman in their Elizur-Weidman text. Then there are reverse measurements, which is, I think, are being used these days very frequently. And there is research going on this reversing operations these days a lot. And also measurements that can use indefinite causal order. So
the last topic you have mentioned, I mean, And there's so much what's already done in the last topic.
Yes. The lot has been done in this indefinite causal order.
No. With measurements.
Yes. I think the group by Chirivella has a lot from measurements, operations, channels, and everything within indefinite causal order.
No, channels is fine.
Yeah.
Operations are fine. But like measurement, which is the Chris non-preserving for those kind of stuff, I have seen only a few, some by TV,
Yeah.
some by Masashi,
Yeah.
and there are only few which actually specifically within this topic, but not much.
Okay.
But yeah,
Maybe there could be more. Quantum measurements are of interest in theoretical understanding of quantum physics also. We know the measurement problem, which is an open problem, but I will not go to any philosophical discussions about it. I will only discuss the problem with a consistent formulation of measurement and implementation in physical systems. So the quantum measurement is fundamentally known to disturb a quantum system substantially in general, and this poses a barrier in extracting the exact information about a quantum state by the quantum measurements. As a result, attempts have been made to minimize the disturbance by varying parameters, taking help of quantum memory and the formulation of fundamental limits, such as the measurement disturbance relation or the preparation uncertainty relation, which is conjectured to be less than the measurement disturbance relation and yet to be proved rigorously in general. So, this is developed to an excellent degree of precision in non-relativistic case. In relativistic quantum mechanics, for example, which involves the Dirac equation, or even in the quantum field theory formalism, the quantum measurement formalism is still not developed rigorously. So this is a really open area. And quantum measurement formalism in relativistic quantum region still has some even fundamental issues that needs clarification. And the issues of quantum measurements in the relativistic regime is connected to various other problems that lead to some form of inconsistency or a need of clear formulation. So this is involving the definition of a reduced spin density matrix in inertial reference frames and spin correlations or spin statistics in those frames. As a result, the quantum measurement formalism needs to be extended to relativistic regime in a clear and consistent manner. So this is, of course, a very simplistic representation of a quantum measurement. So let's go to the strong measurement. Strong measurement is the one which was developed in the first few years, and it's where the coupling between the probe and the system is strong. So projection measurements are strong quantum measurements, and the quantum states are changed drastically after the action of strong measurement on the quantum state. For example, the pure quantum states act as projection measurement operator representing the strong quantum measurements.
But from projective measures, each type of medium is a strong measurement.
That I think I have to. We can discuss it after the talk. So, those weak measurements, there are usually two different.
Weak measurements are
Yes.
pure weak, but
Yes,
weak
yes.
is not strong.
So this is, we know that I think all of you are here at quantum information. So we know that this is the map formalism for quantum measurement. So this is what I discussed already. So apart from the concept of strong measurement, the concept of weak quantum measurements and the corresponding concept of weak values was introduced by Feynman and Aharonov. The main concept of weak measurement was introduced as a means to think about a procedure that disturbs the state of a quantum state to a minimum. And we have both the pre-selection and post-selection of the quantum state. We take into account both of them, and we at the end we get an expression for the weak value. So This is using the two-state vector formalism proposed by Weidman, Aranov, and I think there was Albert also here. So this is another form of measurement. This has many applications, which range from quantum state estimation to quantum state smoothing, which I will mention present in my result. The other applications of weak measurements, like that of quantum state smoothing, involves the use of continuous weak measurements. That is, weak quantum measurements done sequentially with almost vanishing time gaps between them. As a result, weak measurements allow the continuous measurements of quantum states without the Zeno effect, which is freezing of the quantum state repeated application of the prediction measurements. This gives one the opportunity to extract quantum information from a quantum state for a prolonged time and sometimes with improved accuracy. Another aspect of quantum measurements is called the reversibility. Okay. Corresponding to different types of quantum measurements, like the pure wave measurements in general or the weak measurements, the element of reversibility comes into play accordingly. It is therefore important to fully characterize the role of quantum measurement in encompassing information gain, state disturbance, and reversibility together with their fundamental relations. So the equations that involve all the important features of a quantum measurement, such as the information gain, state disturbance, and reversibility, can provide a useful guideline for designing a quantum measurement in accordance with the aims of quantum information processors with high efficiency than before. So it will allow us to choose some optimal measurement settings that can have the maximum information gain with minimum disturbance, and where also we can have a operation which reverses the effect of the state disturbance. So in those cases, these relations will be helpful. And rigorous practical benchmark to optimize measurement-based quantum information protocols can also be derived from some relations.
So, what exactly is meant by reversibility?
So if you have a quantum state and you do a measurement, the state is changed. Now you can have another operation, you can design another operation and act on this changed state, which will recover the input state with some probability. Okay, so it partially reverses the state disturbance.
Does it depend on what the outcome thing? The process to reverse the thing? Does it depend on the outcome of the measure?
Yes. Let us state here the basic definitions of the concepts mentioned in the previous slide, that is information gain, quantum state disturbance, and reversibility of quantum measurements. So information gain, the amount of information obtained by M can be quantified based on the overlap between the input state psi and the estimated state psi r. Okay. So this estimation strategy can be anything. And the estimation fidelity is obtained by averaging this quantity over all input states and possible measurement outcomes, which is different values depending on the estimation strategies. And the information gain is defined as the maximum estimation fidelity. So this is the best possible scenario over all possible strategies. The information gain, this can be proved mathematically as this range. And the upper bound is reached by a von Neumann measurement, and the lower bound is reached by a unitary operator. So they take this formalism takes all kinds of operations that involves measurements as well as the unitary operation.
D the dimension of it.
Yes. And then there is a quantum state disturbance. So these are defined operationally in the sense that there is an estimation procedure in between. And in order to quantify the amount of disturbance by a quantum measurement, we consider the operation fidelity. The operation fidelity of M is given by averaging the overlap between the input and the post-measurement state psi r. Then the maximum of operation fidelity is calculated, denoted by F, and the measure of disturbance is given by this quantity. It also has some range. And then there is the reversibility. We consider the subsequent of the reversing operation R, which faithfully recovers the input state. Okay. Assume that the operators, so there is some nomenclature for these success events of this operations, and this gives the success provides gives the success probability of the reversing operation when the outcomes are. And so this is mainly quantifies what I told conceptually what the procedure of reversing operation is. And there is this is the bound for this operational notation. So this work was done by my supervisor at Korea. So there is this three inequalities. So this was published in Quantum magazine, this theory part, and this says the complete information balance in quantum measurement. The following three relations characterize quantum measurement process. So this is the information gain and quantum state disturbance, and all these things are defined operationally. This is reversibility and information gain, and then there is the three together: information gain, state disturbance, and reversibility. So this was a very new thing. It's kind of a bit like uncertainty relation in the similar sense, but it's a completely different relation. And then diagrammatic, we can see something like this. So there is information gain, disturbance, and reversibility. So this is the one relation, the GR relation. Then there's the DR relation. And then there was a GD relation. So, and then this is the new one, the most novel one, which includes the GDR together. Okay. So let's see diagrammatically. So this is the quantum measurement, then there's a reversal. So what says input state, then there's a measurement, and there's out arc. And from this measurement outcome around, there's an estimated state, tilde, and from where we get the information gain. And then there's a post-measurement psi r, on which the reversing measurement is done RL, and it also have the psi RL as spider. So where it was done recently, actually, it was published in Quantum Journal, and then there was an experimental verification in the same group at East where I stayed. So they published it in PRL, so they got in the cover page, and there was some news about it. So this is a very novel equation that was derived recently.
So what was L there?
Yes, I go back to this equation. There is. Should I go to the next slide? So I now go to those were the background.
Reversibility of measurement, why do you do it? In what context do you do that?
If we want to, there's a possibility of using less resource of a quantum. We want to use the quantum state many times, and we want to get the as close to the input state as possible as much as possible. Then we can use the reversing measurement on that. For example, we did an application in entanglement swapping protocol. After the measurement, if we apply another reversing measurement in between, then the entanglement swapping protocol efficiency increases for 25%.
Does not have any universal carry. It depends upon what measurement you are performing, what is measurement outcome based upon that design the reverse process.
Yes.
Do you have some partial information on the input state? If you do not have, then how are you reversing that?
We have the measurement outcome, right? We are reversing.
We can choose any state from the block here.
Yes.
And we are doing the measurement. Once
Yes.
the measurement is done, then the information about the input state is completely lost. Apart from the measurement outcome, you have no information because state will collapse.
But we have an estimation of the state, right? Psi r tilde.
I don't understand what is distinction. Okay, anyway.
We, from the measurement outcome, what we get the measurement outcome, we have an estimation strategy to infer about the input quantum state, which is psi or tilde.
Yeah, but for that, you have, I mean, you should have some partial equation.
So that gives some, that is what is the state estimation, that's what we know about the quantum state. So that is the measurement outcome already gives some partial information about the quantum state, and you have to design a proper optimal estimation strategy to derive all the what the input state was based on the measurement outcomes.
Anyway, we can discuss.
So the estimation strategy protocol is already trying to extract information from the input state.
Substance. Modify to reverse.
Yeah,
One more question. So,
yeah,
you know, when you talk about the black hole information paradox, where because of whatever falls under black hole, the only thing you get to see is the radiation, where you don't have any information about the. So now, that is a kind of equivalent, that process of the radiative state is equivalent. The equivalence one may think of as a measurement by the environment on the system, that is the kind of measurement. So if I do this reverse process of it, and I get some information there in the input state of black hole.
that is the important question. Actually, this was also my professor also wants to explore this area of black hole information paradox in this formalism. Can we know partially about what was, or if all the information is lost from inside the black hole, or
No, because it depends only on the mass. So whether you throw apple or the mango, that information is lost.
Cross. Yes.
It only gives the information
no?
of
Which
mass.
I'm asking, like,
How
what is the amount of information
Radiation.
you can infer?
But the amount of radiation that
Yes.
will be coming out through, I mean, an amount of information
Yes,
that will be coming out through the radiation.
yes,
So that depends only on the mass.
yes. That,
But-
that
but-
depends on the mass. Then do you have some partial information about the mass?
You have the information about the mass,
So that is partial information.
yes, but you cannot distinguish between these two things.
So that's complete information, right?
Yeah, mango of the same mass or apple of the same mass. That
Yes.
distinction you cannot. In other sense, what is the exact quantum state of the input? That distinction you will not be able to.
Yeah.
Classical
Partial discrimination.
There is only classical description. The quantum descriptions include the hair on the network and the partial information. That's why, I mean, a classical black hole will never, you cannot construct it. Yeah, but it's not classical.
That is not a classical description. Whatever is that you collect information from the radiation and you can be construct. But I'm not.
Last
sorry.
two radiation
Construction?
Yeah, there is a product. If you have a qubit.
Yes. It depends on other characteristics. So that's why these are absent in classical. I think
Maybe there is, there is this Schwarzschild black hole people talk about, where in the horizon, but that event horizon. So some people say that some information about whatever has been fallen inside black hole might be there. So that's like measurement, standard measurement. Where does the information go? Basically, it goes into the environment, like the measuring apparatus of particle. So similarly, if some information is there in the horizon, event horizon, maybe there is a possibility of extracting. So it has not gone inside the black. But I don't know this, whether that is.
That is a more here, it's a classical. So, in that case, there cannot be any such. Pyramid.
But in the quantum domain, how do
So they construct these, there are firstborn. So eventually give more features to black hole than just the.
we are saying you be basically, you have to know what it is.
Quantum.
All the member collection of qubits as well as the apple as a collection. Getting going into the black hole and just connect the function of the radiation. Then you apply the gas model. Apply the base recovery. And you essentially get.
Part of the paper.
I don't know how to define.
That model was not the classical model. Starts from that quantum physics.
Maybe for them.
Anyway, it's fine, you know, you can,
But yeah,
sorry.
So, yeah. So, I'll now state some of my results. So, this was done in my postdoc when I was in Tel Aviv, but I worked with some people in India. So, where we introduced the inferred variance uncertainty relation, and this is actually involves use of quantum measurements on the part of quantum memory, and uses quantum memory and quantum measurements on that quantum memory to infer the results at a distance party. We know this is closely related to steering, but this relation with these how this measurement uses the entanglement and the correlation between these parties was not developed. So we gave a new uncertainty relation based on this. So we devised a measurement scheme using quantum memory such that the uncertainty limit conditioned on the quantum measurement on the memory was reduced significantly, and it could give us a precise value of two non-committing observations with certainty in some cases. And this was also the first to show that how an entanglement measure is responsible for reducing the uncertainty of two non-committing observables with judicious use of quantum memory and quantum measurements. This is found application in entanglement detection and quantum cryptography.
Quantum memory.
Oh, okay. So this is quantum memory. I just said that there is there is another party where these two parties are together entangled together. So that's what we operationally call a quantum memory.
So what exactly we are measuring here? How is it?
So we want to infer the values of two non-committing observables. How much precisely can we do that? With normal quantum mechanics, there is an uncertainty relation. But when we use another party, and which is entangled with this party, so taking information from the measurement performed locally from one of the party, and the fact that these two are entangled together, the other party can infer the values of two non-committing observables perfectly.
Perfectly.
Yeah, in for maximally entangled cases, but for non-maximally entangled, we can reduce the uncertainty, which is dependent on for example, this concurrence, the entanglement measure, the concurrence, or there is another entanglement measure for mixed quantum states, which is related to this some correlation.
What is actually happening here is because of the existence of correlation with another party, incompatibility of observable getting reduced. What is happening?
No, the incompatibility of the observable is not reduced.
I'm not saying effectively with at statistics level.
Yes.
Is it the case that because of the existence of correlation with another party,
Yes.
you are saying that this is memory and that reduces the uncertainty?
So I don't know if you're talking about the incompatibility measure, but or non-commutativity or commutativity relation.
No. When you say that uncertainty relation, standard uncertainty relation will pose some lower bound,
Yeah.
that product or whatever it takes,
Yeah.
uncertainty relation. There's a lower bound, which you cannot cross.
Yes.
But when you say with the help of memory, I can even go further.
Yes,
So what does it mean? Does it mean that because of the existence of correlation with the second part,
yes,
with some ancillary,
yes.
somehow the observables for which you are looking for the uncertainty,
Yes.
they are becoming more compatible or what is happening?
I would infer it in this way that because we have more information or more resource because of the quantum memory, so that is an extra resource. That resource is helping us to predict the values of this not commuting observables more accurately. That is how I infer. But I don't think with mathematics. I mean, not commutative, as I understand, it's just a commutator is some something.
No, that is okay, but operationally what is happening? You know, is it that the because of existence of memory? See, when you talk about incompatibility of observables.
Yeah.
Then I know, you cannot have joint measurability, cannot have joint measurement statistics, whatever the way you want to call it.
Yeah.
So that property effectively is reduced or what is happening here? Why is uncertainty? The bound is reduced.
So
Now,
first,
people use this uncertainty relation, for example, for testing entanglement.
yes. So this inferred variance. So this, for example, this delta S squared, this is inferred. So this variance has a bit different definition from the normal variance.
So
Yeah. Because this is based on the conditional measurement results. So
I'm not just talking about this particular relation.
Okay.
People have used this memory and use that this
But-
Mario Berta.
but-
So they have also used something like memory and to reduce the uncertainty.
Yes.
I don't know when was that. Yeah, so essentially what is happening? Why is it the case that in the presence of memory you can reduce the uncertainty? That is what is happening.
Yes. Yeah.
Anyway,
Yeah. Maybe we can discuss. So yeah. So these and there were more results of this, which also included quantum discord. But now I just mentioned, and then we didn't work on this reverse uncertainty relation because we want to extend this for the same course of quantum measurements. And we derived state-dependent upper bounds to the sum and product of variances using the reverse Cauchy-Schwarz and Dunkel-Williams inequality. And this our results suggested that not only we cannot prepare quantum states for which two incompatible observables can have sharp values, but also we have both lower and upper limits of the variances of quantum mechanical observables on the fundamental level. So this was published at the end of my PhD. So we still are continuing, because I say that because we are still are continuing along this direction. The implication of this is that in a similar way we can find a reverse measurement disturbance relation for quantum measurements for finite dimensional Hilbert space. With infinite dimensional Hilbert space, there are problems of infinity or some singularity problems in this formalism. And we keep this as future research direction. This will help us in benchmarking the efficiency of quantum information and computation protocols. And this has also been experimentally verified. So we can use this upper bound also to benchmark the efficiency of certain quantum information protocols. So this is actually a future direction of research that I have started, but we are continuing, but probably it will require more time with this one. So this was this actually got highlighted in Nature India, and this was also experimentally verified in 2020. Yes. And Now I move to this inherent information loss with the work that I have been doing with my advisor in Korea Institute of Science and Technology. And we mentioned in the previous slide, what's the time? Okay, 4:15. We mentioned in the previous slide about the triple trade-off relation between the information gain, quantum state disturbance, and the reversibility of quantum measurement. This is called the triple trade-off uncertainty relation or the complete information balance. So here we ask one of the most fundamental questions in quantum theory: what is the loss of information in a quantum measurement, which is yet to be clearly answered. And based on recently established framework of complete information balance, we quantitatively define a novel quantity measuring the loss of information in quantum measurement. We name this the inherent information loss in quantum measurement. And as Professor Ghosh said, actually my advisor Siang Lee, we have the results, and he is writing the paper. He also wants to involve some amount of some comments about black hole information loss paradox and no hiding, its relation to no hiding theorem. So Professor Hall already said that, so I think it's clear that there is a relation with that topic as well. What is trade-off? Triple trade-off that I showed, the reversibility, information gain, and disturbance.
Is it the work you have done with bottom? Bottom?
No, I have not worked with Gautam. This is with this is yet to be put on archive. This one. This actually we are still thinking that if you want to connect with to quantum classical transition also. So yeah, so this has connections in those areas as well. This information loss is originated from the inherent non-optimality of quantum measurement, which is fundamentally differs from the loss of information by decoherence or coarse graining of measurements alone. But probably this information is stored somewhere in the environment because there is, the no hiding theorem. So, yeah, those are still being included in the writing of the paper right now. So we first introduced the model for investigating the loss of information by quantum measurement. Suppose that an arbitrary quantum state rho enters into a box where an observer performs a quantum measurement in. The quantum state rho contains all the information and the observer intends to extract the information via n, which eventually disturbs and changes rho to another quantum state. At this stage, the observer can apply a reversing operation by modifying the measurement setup to recover the input state rho, that is to restore the information at the output state. Here, the box is assumed to be able to protect any effect of the environment. So, how do we define this? Let us now define the loss of information by quantum measurement alone, irrespective of any environmental decoherence, completely independent of that. For a given quantum measurement, we quantify the loss of information as the shortest distance from these cards, IG, IO, and IR. Well, these are the three relations that I showed involving the triple trade-off, that is F, D, and R. This is one card. I think that for the next diagram it will become clear. Okay, so and then so L is a minimum distance from one of these cards. Okay, and XM and this are the distance from XM to these three cards. Okay. And so this is the information gain. This is the reversibility and this is the state disturbance. Okay. So let us illustrate this with a simple example. For example, take the case of a qubit. And we have a qubit measurement when we d equal to 2. And then the trade-off, these are the trade-off relations. I hope this is clear what this means. Information gain, disturbance, and reversibility, the 3 trade-off relations. We rescale these variables and they can be written like this. For qubit case, it becomes very simple. And then DGD is the distance from this to the curve given by the equation. So this is the point, okay? IG, IO, IR is a point in the parameter space. And the DGD is a distance of this point from one of these curves. Then this is the distance from another curve, and then we take the minimum of all these distances. And for qubits, we get an analytical relation like this for inherent information loss. But this is the information gain, this is the reversibility, and this is the state disturbance, IO. So I just show in a very simplistic version. Suppose this is the point, okay? And this is for high dimension. I show in a diagram by diagrams. This is for d equal to 10, k equal to 10k is the outcome of the measurements. So this is one of the distance, and this is for another dimension. This is another case. Then there's a second inequality. Then we find the distance like this. And then there is a third inequality, because now the third inequality involves 3, you know. So now we have a high dimensional diagram. So we find distance from these curves. And for very high dimensions, it was not possible to solve analytically the expression for the distance, because to have the minimum distance, then you have to perform the first of all, you can have the calculus of variations, and when you do that, you get you have to solve because of the nonlinearity of these cards. You then have to solve polynomial of degree, a very large degree, 6 degree or 8 degree or something like that, which is analytically not possible. In those cases, we do it numerically. So for a very large dimension, for example, k is equal to 100. So for lower dimensions, we did it analytically, but for large dimensions, we did it numerically. So for k equal to 100, and this is with increasing dimensions, this is what the nature of information loss looks like. So we want to get a physical intuition from this trend.
What does it mean? What is the place?
I'll come.
How do you do for what?
What?
What is the for what and
Just normal Lagrange multiplier method. Yeah, calculus of variations. Yeah. And this is also information loss. This is the number of measurement. And then there is the dimension I showed before. So we see in the information loss, inherent information loss get very narrowed with increasing dimension and very peaked with increasing dimension and with increasing number of outcomes. We see this trend in all the numerical things that we see. We have performed, I just showed here 2, but we perform many, and we see this trend everywhere. So we then ask the question, like, for lower dimensions, we can see what is the trend, but why this trend follows? So we ask this question of why is this happening? And then
What is what it is physically you were saying? What is inherent information?
Inherent information loss, information, there are process of information loss. When you do a quantum measurement, the state is disturbed and then the whole process that I mentioned before, and you cannot recover the state fully, and there is loss of information because of the non-optimality of the quantum measurement, and not because of environmental coherence, not because this environment is getting entangled or it's getting discarded, the ancillary is getting discarded, or some noise is being added because of none of them, just because the quantum measurement is not optimal. Optimal in the sense meaning it doesn't reside on any one of these trade-off relation cards. Yeah. So there is an inequality and the equality is not saturated. That's why this stays on the card. Those are optimal measurements. And the non-optimal measurements are those where there is the inequality, that the equality is not saturated and it's inside one of those spaces and it's a non-optimal measurement.
And those, for those non-optimal measurements, whatever the information loss you are having, that you are calling inherent information.
Yes, because this is inherent to the quantum measurements and not because of any outside effect.
I mean, I understand what you were saying, but the point is like interpreting things, it's like a new kind of information loss I do.
Okay, so I haven't actually seen anything around, but maybe we can discuss it later.
Yeah, so point is like, I mean, you are doing a measurement, you can also interpret in terms of big moment. So I am just not very clear to see like what is the physical ingredients of inherent information. That is my precise question. Right.
You can definitely describe it in terms of the environment. For example, a POK has a projective measurement, you have an ancilla. But when is it actually the physical process that is happening? You can think of it like that.
I mean, even if you do projective measure, essentially you are doing some form of physical process of this. That period. Even projective measure.
Yes.
Whatever it is.
Yes.
Essentially, you are performing using some physical setup. Using some physical setup.
Yes.
I mean, yeah, probably what I'm not very clear to see is that what is the inherent information loss in terms of physical system. Right. I understand you are quantifying it in some way, like the deviation from the optimal measurements.
Yes.
Yeah, maybe we can talk about that.
Yeah, I think
Maybe in the technical talk.
yeah.
When the recovery exists, where does it exist for all?
No, there are operations where the reversibility is zero.
Cannot construct that.
No. So it's the bound is between 0 and 1, reversibility. So reversibility is zero means there doesn't exist any such reversing operation. Huh?
And one is
One is there is full recovery.
like, do we know exactly what are the conditions? Given I give you two states.
Yes, we can construct that. There are very well known operations which we know that the reversibility is zero and less than 1. So it's related to projective measurements and unitary operations. So we know some cases, but given a quantum measurement, the POV usually has some value in between 0 and 1. The 0 and 1s are saturated by projective and unitary operations. So we analyze the patterns of the plot of inherent information loss. The pattern we observe that the value of the peak of inherent information loss increases with increasing the measure. it gets more peaked with increasing dimensions and number of outcomes. If you notice this pattern, we realize that it has close resemblance with the properties predicted by the Levy's lemma. And therefore, we apply the Levy's lemma by mapping the quantum measurement operator sets to a parametric point on the n-dimensional unit sphere and then apply Levy's lemma to the set and successfully explain the statistical feature of the sharpness of the peaks with increasing dimensions and length outcomes. So the proof is, I have not given it because it's technical, we can discuss, if anybody is interested, we can show it. But we have used this thing to explain the numerical pattern we see with increasing directions and increasing outcomes for this quantity of inherent information loss.
So when you are increasing dimension, that means your information loss is also.
Yes, it is more and it is spread out. Less spread out. It is more concentrated towards the mean value.
Concentrate. That is a concentration. But okay, that is clear enough.
Yeah. And so we know that what is the Levy's lemma if it's in n-dimensional unit sphere. So let's just look at this formula that probability of it satisfies some conditions, the continuity conditions and all the stuff, and there's a selection of uniformly at random, and there's a probability of this effects concentrating towards the mean value. So this n function is actually dependent on the dimension and the number of outcomes in our case.
So
And we-
concentration is happening around the mean that is coming from the Levy's lemma, I can understand. But
And it is dependent on the value of the dimension and the measurement outcome, which is inside the value n.
why the information loss is also high in the high dimension, that,
This is information, inherent information loss.
right, so it gets peaked around mean that I can understand from the concentration, like Levy's lemma.
Yeah.
But
If it is getting big, but if this is getting concentrated, it will also be big. If
So
we
you're saying-
conservation of probability.
so you are saying that with all dimension, inherent information loss is also considered in some sense.
No, I think we haven't looked at that, but
Because that argument only applies when you have a.
we have the same area under the
Same idea.
diagram.
Yeah, that's what.
No, I think it is true. Yes, there is a bound of the inherent information loss. When we all use all the scale normalized variables here. So I think there is a bound of that. I don't remember the bound. I can show it. There is a upper bound of that, and that is the reason that yeah.
And whatever the reason I saw on the.
Where is where?
The second maximum.
This data actually lift its continuous. We proved that this inherent information loss is lift its continuous function. The lift its continuous geometry is a bit different from the normal continuity. It has finite parameters which comes in the definition of continuity. So we saw that this and we proved that. If you want to see the proof, I can show it in our draft.
Not a continuous form. The Lipschitz.
Lipschitz continuous, yes. Yeah, so the function of the inherent information loss is quantified by distance from one of the optimality curves in Lipschitz continuous. And yeah, so this we showed rigorously that using the Levy's lemma, we explain all the pattern of inherent information loss with dimension outcome. And it can have some relations with randomness of quantum states or entropy of random quantum states with increasing dimension. I think there is some results on that. But this is still mathematically we have not proved it, but it can have because it follows some kind of similar pattern. And also there are some relations that Professor Kothal said this connections with no hiding theorem or the actual information loss paradox. So That part is still work, we are still trying to add to our draft. So, yeah, it's a bit of work in progress, at least in the interpretation stage. So we show that there is an intrinsic information loss in quantum measurement absence of any environmental requirements. It's a direct consequence of the non-optimality of quantum measurement. It increases with increasing dimension and for coarse-grained measurements. So this is I already showed. Yeah. So this it may have some bearing on the fundamentals of quantum theory, such as no hiding theorem and quantum to classical transition also. So this is because quantum to classical transition has been proved using the coarse graining of quantum measurements by some people. But what Tianguli thinks is that he can also explain it using this non-optimality of quantum measurements in inherent deformation laws, which encompasses the coarse graining of quantum measurements. And there is something extra. So this part is what we say that this is what this quantum classical transition part is working towards right now.
What exactly is no hiding theorem?
I think no hiding theory is just if you discard a part of the information, the information is stored somewhere in the environment, as far as I remember. So there's no hiding. I think the information is not lost, but it just hides in some subspace of the environment. Yeah.
It gets lost within the environment.
Yes, it just stays in some subspace, not on the system.
So in the quantum to classical transition, let's say via these post-grain operation, that is one way of. So how does this triple relation modify? So what is it that we expected? It will go more towards non-optimal regime or what?
Yes, it goes towards what we are thinking, but we still have to prove it rigorously. But what we were thinking about this is that because the inherent information loss also increases with force draining, we increase the force draining, and this is close to what the classical quantum to classical transition have been proved by some people by increasing the force bearing of the measurements.
Yeah, so basically, there are several ways of understanding quantum to classical. One is to size, increase the size.
Yes.
The predominant one is you take gauge values, which is not always true. Other possibility, there can be more, is that you look at your potentiality of distinguishing objects or distinguishing states. So by post-bending your measurement more and more, if you still can distinguish, then it is a process of going from quantum to classical. Like, you have macroscopic objects for which you don't need microscopic measurement. I mean, you don't need atomic. You can post-grain, you can.
Okay.
So this post-graining of measurement is one way of understanding quantum to classical.
So what here is first of all, the increasing dimension is also increasing the size.
Kind of, not always, but it does not mean that if I increase dimension, I'll always come up with classical.
And then along with that, there is force graining. So this is I think what we will do is we will look at the patterns. We have seen some, for example, we have looked at the patterns of the CGLMT inequalities or variation of weighted body inequalities with this quantum measurement models by increasing force draining and connections with the inherent information loss. But we still have to form a good theory, polished theory to But this is a potential direction, but this work is still in progress, this quantum to classical transition. So on the level, I just said that the pattern of the inherent information loss with force grading or increase in dimension has that's from where we are thinking we can explain this class on the quantum transition, quantum to classical transition.
This inherent information loss will decrease as we go to classical reading, because classical reading we don't have any such inherent information loss when we do.
But I don't know the scale. I mean, classical is what the
I mean, you can always measure anything without discovering it.
I think this will really require a more thorough analysis. I mean, I really don't think I can sweep everything under one bracket. All the conditions. Not now. When we have more conclusive evidence of this I can tell more clearly.
This time we take.
That
it's like your inherent information loss is of classical.
is of classical nature.
You have optimum quantum measure, which can be on the which can minimize everything. Triple trade-off you have. So that triple trade-off, if you can perform that measure, then everything is optimized. So you will not have any inherent information. If I am saying correct or not.
Maybe I should finish it
Maybe.
first and we can discuss. So this is, I just mentioned the proposed scheme for reverse measurement in entanglement swapping protocol. And this is the increased, so this is an application of a reverse measurement, and there can be, we can come up with ways, one would be to have given a measurement or estimation strategy can be devise the optimal reverse measurement protocol that would be useful. So those are the directions that can be pursued. Oh, this is the quantum state smoothing with big measurements. So this is I'm doing with my own students. So it uses this two-step vector formalism and a theory of continuous weak measurements. So one of the applications is the task of quantum state smoothing, which uses information from both the past as well as the future measurements for the estimation of quantum state with improved accuracy. And we apply the theory of generalized two-step vectors to the task of quantum state smoothing. It will, what we have done until now is derive an expression for the smooth value of the estimated state in terms of generalized weak value by using different setting for quantum state smoothing, analyze cases where we can take superpositions of prediction and retrodiction together, and this improve the quantum state smoothing protocol. So this is still we are writing the paper. I'm writing the paper with the students, and it will come in 2 or 3 months maybe. So I'll just go because I am. So the main smoothing is that we are doing, there's a quantum state and we are doing continuous weak measurements on the quantum state. And we have past measurements and future measurements, meaning we have continuously measured the quantum state using these continuous weak measurements, and we store the results in a box. And we estimate the quantum state in a time which is intermediate to the TI in TF. So that's what we mean by past and future quantum measurements. So in classical systems, this smoothing is very well developed, but in quantum systems, it's not. Because very recently, this group by Howard Boyle, and they only come up with a formula for the smooth quantum state, which preserves all the properties of a quantum state. And so this was also work done by Justin Dressen's group in Chapman University. But the new thing that we did here, we use generalized two-step vectors, and we do not discard the ancilla. So in generalized two-step vector, we do not discard the ancillary at every step. We make an ending post-selection measurement keeping the same ancilla. In this way, our resources for ancilla is also saved. Not only this generalized two-step vector is really resourceful, which will help us in attaining better accuracy of quantum state smoothing with less resources. So this is one expression that we derived. This is the final expression. I just show this probability distribution of a readout R given the past record, future record, and this quantum state rho. So we see that there is this weak value. That's the weak value, and there is another value which is not weak. That is not the weak value, but another value. But we see that this is the weak value that we have in the two-step vector formalism, and this is the quantum state estimation using past and future measurements. And so this is what we call the epic matrix, and this is the past matrix. And this is for 2 qubit states. This expression for the probability, and there are some experimental parameters here below here. So we are now at the stage of performing numerical simulations using different examples in questions, but we have discussions with my advisor at KEST and Professor Weidman. And future direction is that we want to do quantum state smoothing for 2 or 3 non-committing observables together using generalized state vectors. And there we want to, this is with the same thing with the students in connection with quantum sensing protocol with past and future measurements. This will be something new. And so these are my own projects that I'm doing under some program. So and then there is another application of weak measurements, where with pre and post selection, we can modify the interaction between 2 quantum systems. We can change the repulsion to attraction, attraction to repulsion, and even effectively, we can switch off the interaction between two particles using proper pre and post selection and quantum measurements in between, and sometimes even a bit stronger measurements than the weak measurements. And this is Professor Weidman's his own idea. So this is also almost a finished project, but experiment will be added to this. So this is with Professor Weidman right now. So this is another application of some clever use of quantum measurements using pre and post selection, where one can have a modification of interaction between 2 particles, and it has a potential impact on experimental physics, which adds a new more feasible way to manipulate several interacting particles together. So I'm actually really some other people out there, so I'm acting as an academic editor of this quantum computer. And these are the projects that I am working on: quantum sensing and quantum state smoothing. With 6 students under it, and then there's the reverse Lorentz in quantum metrology, and also 6 students. So these are some applications that I'm working on. And this quantum measurement with relativistic effect, this is one fundamental issue that I think that really needs to be addressed. The majority of current understanding of quantum correlations in the field of non-relativistic quantum mechanics. To develop quantum information and computation tasks fully, one must inevitably take into account relativistic effects. So the spin is one central tool. However, there is the concept of spin and spin quantum correlations in inertial frames, which still have some paradoxes, and even like with 0 acceleration, but with velocity, there is finite relativistic velocity. Even that, the concept of spin quantum correlations or the spin reduced density matrix is not formed, it's not done yet. So this is one area which is really doesn't look really something extremely big problem, but still this needs some resolution. And the problem with quantum measurement extend far beyond the domain of non-relativistic quantum mechanics. The problems of quantum measurement extend to relativistic scenario, with even more fundamental problems as added to the existing issues of non-relativistic quantum measurement problem. There is no reconciliation between causality, special theory, even special theory of relativity, covariance and the generality of relativity comes so much later, but even in the more simpler case of special theory relativity, there are problems. And these are open issues that can be addressed in a much longer run with time method. So this is a book chapter that I wrote in. I was invited to write this book chapter, Quantum Entanglement in High Energy Physics, and I wrote it. It's close to publication now. And this deals with this was a review prior approaches to spin in quantum physics and promising approaches that can resolve this. And then this will be, helpful in future spaceless quantum technologies. So this is the book that is going to get launched soon. And this is another problem that I'm working on, this Bell non-localating network, devising quantum measurements to to distinguish between classical and quantum correlations in triangle network with no input but with binary output. And by Bell non-localating triangle network, this is in the intermediate stage. We have some preliminary result, but we need to work on it more. And that's it. So, conclusions and future directions. We have covered the basic notion of quantum measurement and applications in various ways and forms. We discussed some fundamental limits of quantum measurements involving unscientific relations in its present form, and also potential future directions involving reverse unscientific relations or reverse measurement disturbance relations based on some quantum technological efficiencies. We have discussed the inherent information loss in quantum measurements resulting due to non-optimality of quantum measurement. It is not a result of environmental decoherence. We presented its analytical form, proof, and numerical solutions to present our results. We have then discussed the concept of weak measurements, continuous weak measurements, present and future measurements, and its important application in the task of quantum state estimation and quantum state smoothing. I presented my current work and future directions that result. These students are just under me, not with my KISS supervisor or even with Professor Weidman. And the reverse quantum measurements have been used to improve the entanglement swapping protocol. And there can be more uses of reverse measurements in future. And relativistic ethics, that is what I discussed. That's one of the foundational problem or fundamental issue. Sorry, this is a typo. I have presented certain areas of reduced spin quantum correlations where a good relativistic description of quantum management will be helpful. And this will be helpful in space-based quantum technologies. And so all in all, I present a kaleidoscope of the uses and fundamentals of quantum measurements that are not only useful in various quantum information and computation tasks, but also in understanding of nature in the long run. And so this is a acknowledgement that is supported by this National Research Foundation of Korea. There's a ground grant numbers, and there's this institutional program. And so that's it. Thank you.
So you would have the you can, but also what is the inherent information was, is that understood correctly? So it is our to quantify it by saying that you cannot perform the optimal quantum measurements, and the deviation from that you are quantifying by. Am I right?
Yes.
So if you can perform the optimal one, then inherent information loss is zero.
Yes.
So that means.
So the distance, the point lies on the card. If it's optimal, the point lies on the card. So minimum distance from one of the cards is zero.
Sure.
So the inherent information loss is zero.
Yeah. So when when it is non-zero, that means you would have in principle a measurement which can make it zero, but you are not performing or probably even not able to perform. In principle, every time I can make the inherent information loss. We have a measurement setup, but we can use it as a two-step method.
Given a quantum state and so it's a measurement a property of the measurement. So, if you say that we can find a measurement, so then it doesn't really state the property of the measurement, right?
But let's say the proof of existence.
Yeah.
There is the optimum measure.
Yeah.
Which can make the inherent information loss.
Yes.
So now if you have the information loss, let's say you are confirming some measure and there is some inherent information loss.
Yes. Yes, we will always try to find an optimal
Yeah.
partial.
So if inherent information loss, what you will conclude? You will conclude that it's not quantum method or it is just your ability to perform the.
But is it always possible to find, suppose you are doing some quantum information protocol. Okay. So in that protocol, you have certain subsets of measurements and you want to get an outcome. Will you always be able to design this protocol such that the total inherent information loss is zero? Probably not. But probably you can find different sets of measurements which will minimize this inherent information. Point is that this will be useful in designing optimal quantum information protocols.
Can be possible, but what I'm trying to say that it is a classical nature or it is a quantum. Classical nature in the sense, it is our inability to perform. It can be useful that sometimes we don't need the optimal measure. Maybe non-optimal measurement is giving us some better.
But even if we are able to do that, that doesn't really mean it's the classical system.
No, it's not classical system. It's
Yeah.
like okay, probably classical is a great notion itself, but what I'm trying to say is like our subjective limitation that we cannot perform.
Yes, yeah. That can be an important direction, that whether it is possible to, we can think of universally, it is always possible to find an optimal set of quantum measurements. Yeah.
If I was state, can I every time find out?
Yeah, that's not an answered.
Okay, regarding the two-state vector, do you really want to take two-state vector, for example, to describe some physics that you can do in lab, which standard for the mechanics is kind of.
Standard quantum mechanics and two-step vector function always study the same thing. There is no difference in the predictions between these
So then,
two. But with two-step vector formalism, you can what to say, come up with ethics or see certain things in a much easier way, other than using the standard quantum mechanics.
okay, how about the general, what is generalized?
Generalized two-step vector is that you have a preparation, a pre-selection of a quantum state, and you have a post-selection. Okay. So this is suppose we have mixed quantum states. So this applies to mixed quantum states. So the initial quantum state is attached to an environment with the ancilla, and you do measurements on this. We have the pre-selection, and the general and the post-selection is also the environment with the ancilla together, and you get another mixed quantum state of the system, but this is also entangled with the same ancilla. The ancilla has not been discarded, it's the same ancilla. And then, if you calculate the weak value of an observable in between, you will see a different value of the weak value, different from the weak value corresponding to the ordinary two-state vector, where this ancilla will be different.
But that also can be done using standard.
Yes. The weak value, for example, I would say the weak value, this just really comes out very easily in the quantum state estimation with past and future measurements together. But
There was controversy regarding some part of the explanation. Like saying that there is some underlying two vectors.
yeah, but I mean, as we see, or even Professor Biden or Aranav, what do you say, like, introduced this formalism of weak values, weak member, and two set formalism was Aranav with, I think, ABL, Aranav lived with, Barman, yes, Barman. So when I talk to them, they always say, give the same predictions with standard quantum mechanics of the form. There is no contradiction between these two.
That philosophically that problem will be there.
But you are saying certain calculations are easier.
Much easier. You can just see, you know, the quantum states moving the weak value as a moving, I mean, the quantum readout, the readout of the algorithm just comes out as a expression for the weak value.
So for this long time back, there was this thesis by Christopher Fuchs in 96 or something. What was on these measurement and information extraction trade-off. I mean disturbance and information extraction. So here you are introducing another parameter, namely the reversibility. So does there exist a phenomenon which we understand quantitatively in a better way with these three parameter approach compared to what Fuchs has talked about?
Yes, in one, I think I showed there are like three inequalities. One is information gain, disturbance, reversibility, or information gain, reversibility, something of that sort. And then there's this the three involving three. So the triple trade-off actually outperforms one of those two inequalities. I don't exactly remember which, probably information gain and disturbance. It outperforms one of those inequalities. So
Outperforms in what sense?
it gives a tighter bound to information gain and disturbance between those two together.
Yes. And so that is fine. Now the question is that so if I look at this manifold of these three parameters, is it all encompassing in terms of whenever I consider measurement process, or do I need something else?
Given these three properties, the information gain, disturbance, and reversibility, it encompasses all the domain. But I cannot think of any other property of quantum measurement that is to be included inside it now. Is that the question that you know?
I think only for
The probability teacher, somebody will come up with another.
Yeah.
Probably relativistic.
So, if you reverse a state,
Yeah.
is it the same as the, you reverse it to the same state as the one you predicted after that?
With some probability. The higher the probability, the better the reversibility.
No, so I mean, you predict after getting the result, you are predicting the state might be this. So you can just prepare the state test. The output state you can prepare in this predict list.
Output state like preparing the prediction.
So when you are trying to reverse the output state,
Yes.
you are trying to correct for some of the mistake, some of the error that might have the measurement process might have done some error it might have. it might have changed the state. So you are in the reversing procedure, are you reversing the output state to the predicted state, like the
To
estimated,
the input state.
not to the state that you estimate the state after measurement? Let's say you get 0, right?
Yeah, we have an idea from the estimated state. So,
So you know the estimated state.
yeah,
You make the output state and the estimated state.
so let's just go to maybe the formula will make it clear for the reversibility. Here. So this is just the outcome. So this is not the estimated state. And this is the success probability of the reversing operation.
Description for that or you are just getting like this?
Yeah, we assume there is an existence. This is the general principle, but in specific cases, we can design such reversing operations. And we have calculus of probability.
And size the actual state.
Yeah.
Reversing was the parameter.
Okay then, thank Prabhu.
So I thought,
And this is really happening.
yes. এটা কি খুলে দেবো ডাইরেক্টলি? এটা এটা এখানে লাগানোটা খুলে দেবো? এই ইয়েটা পয়েন্টার।
ঠিক আছে, চলো এটা শুক্রবারে আমি করবো। এই প্রবণ আমি গেলাম
হ্যাঁ ঠিক আছে, আমি ফাইলটা তাহলে
আগে ওয়াকড়া হচ্ছে ফাইলটা কোন মানে
So. The board is. Bob is more involved. Bob doesn't have in his near papers, etc.
But hey, it's been nice.
Yeah, man, and events. Okay. That to actually, but let's end it.